Now, I denoted the term a heuristic and I said it should be assumed that your heuristic functions are admissible, otherwise your searches are not optimal. And now I introduced an error in heuristic. So the error in heuristics is, how bad is my estimate? This is what I estimated. This is what I estimated. This is my estimate. Using the above weird ways, this is the best answer. Theoretical, not available. And therefore, this is what is the absolute error and this is what is the relative error. So this is the absolute error, this is the relative error. Let us denote by epsilon of S or error of S. So that's my error in heuristic for the state S. That's how much my heuristic is bad. Now, how does heuristic error really matter? Firstly, this term will never be negative because we have assumed HS is less than equal to H star S for all S. This is by definition of admissibility. So H star S minus HS is always greater than 0. Now, I give you an interesting question without solving it myself, sometimes given in the examination. In the older input, now that you have HS and H star S as a table, so for the older input, which is right here, now that you have got both HS and H star S, so perform the A star algorithm again using H star S instead of HS. So let this entire search, which is right here, be on H star S instead of HS and see what happens. You'll get astonished. Now, what will happen is that you'll get a search path instead of a search tree. And why will you get that? Because any node that you insert in the fringe knows the exact distance from the source and the exact distance from the goal. If you know the exact distance from the source and the exact distance from the goal, you know the exact distance from source to goal. So you never fail, you never backtrack, you never get out, you go into a straight line which is your optimal path. So if error becomes 0 or HS is equal to H star S, the time to search is just linear. I mean, even though you know everything, you'll have to travel the path once from source to goal. So the search time becomes as less as possible. So if epsilon S, which is error, is equal to 0 for all S, meaning HS is equal to H star S, the computation time is C star divided by step cost. Last time we took epsilon here, but of course I've reused epsilon, so let me just say step cost. And that's the least time that you can get. You're just traversing the path. So why don't I do that? I don't do that because the time to calculate this is not constant. The time to calculate this is exponential. This is the search problem. So if you've calculated H star S, you've solved the search problem to make another search fast, but your calculation of H star S invokes all the very troubles. So let's look at the other case as well. What is the maximum error which is possible? I need to maximize the error. So I need to minimize this, which is HS is equal to 0. So my maximum error is when HS is equal to 0. which means Fs is equal to Gs plus Hs. So it's a uniform cost search. And you saw it go around and round and round and round as circles. So this heuristic function with the maximum error doesn't even take the heuristic function. So if I've got a zero error, my computation time is C star by epsilon. And of course, if I've got the maximum error, my computation time is what we calculated the last time, which is B1 plus C star by epsilon exponential. So what is it for the A star algorithm? For the A star algorithm, looking at these two extreme cases, I need to minimize my heuristic error. How do I minimize my heuristic error? By maximizing my heuristic estimate, limited to the fact that I don't overshoot the optimal value. So higher heuristic value, the better it is, the more informed it is, the lesser error it has, provided it doesn't cross this line. The moment in a pursuit of giving very high estimate, it overestimates, then your heuristic function is not admissible at the first place. So yes, you may save time, but you will get non-optimal results. So I need to make in the best heuristic function value which has high value as possible. So my bottom line over here is that best heuristic function gives maximum valued estimates so as to minimize the heuristic error provided, very important, that the heuristic function does not overshoot, or in other words, does not become non-admissible. Now, I'll place another caveat over here, which is, while thinking, many people make that mistake. So, the heuristic function should take lesser time to calculate as compared to the time that it saves. So, very famous in IT, you spend 5 hours to automate a work which takes only 3 hours. So you use a lot of techniques to calculate H star S. You spend in 5 hours. Your search becomes linear. It works in milliseconds. Wonderful. You are so happy about it. However, unfortunately, what about the time that you have already wasted to calculate H star S? That adds. So I should not invest in too much of a time. And what it means in your case is your heuristic function has to be strictly constant. Don't go in for heuristic function that take too long. Otherwise, we'll get into the debate of is it wasting more time or is it saving more time. So, your heuristic function cannot take in too long to calculate. The higher the better. Now it's easy when I look at it over here. Which is the best heuristic function, h1, h2 or h3? This is clearly bad because both these give a higher value as compared to this. Manhattan distance will always be greater than misplaced tile, because if the tile is misplaced, you add the Manhattan distance, which is more than 1. So h2 is always better than h1. And mathematically, we write this thing as h2 dominates h1 because h2 of s is always greater than equal to h1 of s for all s. So h2 dominates h1 because h2 always gives a value which is greater, and therefore it's better, assuming both of them take approximately the same computation time, which is true in this case. Now, if you have for a problem a lot of heuristic function h1, h2, h3, hn, none one dominates the other one, all of them admissible. So all of them are admissible, all heuristic function are admissible. It's a property that is somehow given, and you need to find out which one is the best heuristic function. Some help you can take which one dominates. If you are not getting or none of them dominates, then just take a heuristic function given by hs is equal to max over all heuristic function. So this heuristic function hs will dominate h1s, it will also dominate h2s, max of h1, h2, h3, h4, h5 is always greater than h1, is always greater than h2, is always greater than h3, it's always greater than hn for all cases. So that's an interesting thing. So be very careful about it over here, because if this n is too large, you've got too many heuristic functions. Unfortunately for the maths, you need to calculate all of them, so your computation time may increase. So make sure all of them take extremely small time to calculate. Now, about the general case of the A star algorithm. So we saw these two things around over here. So if the heuristic error is 0, that's my computation cost. If the heuristic error is largest, that is my computation cost. In short, the computational time complexity. Let me take the simpler case, which is for graphs which do not have this step cost, which means the unweighted graph or all the costs are 1. Otherwise, there's a step cost that I am constantly incurring. So the complexity is given by b raised to power epsilon, which is my error, times the depth. So if epsilon becomes 0, then the interesting thing that happens, the complexity is completely gone. You just need to travel on the path. If epsilon error becomes as large as possible, then you see that the error is maximum, which is the optimal path cost. So there are too many nodes in a path, so we take the maximum one. So if this is your path, where did you get the maximum error? And that's what put bounds on this epsilon. So you'd like to keep error as small as possible. Now, given that the A star algorithm has the best heuristic function, it's called as not only optimal, it's called as optimally efficient. Which means you cannot make an algorithm that discovers lesser number of nodes, which means lesser time, and still gives you the correct answer. So the A-star algorithm is guaranteed to explore the least amount of space, give the least amount of computation time. Of course, assuming the heuristic function calculation is a substantially small amount. So, given the best heuristic function, A-star algorithm is guaranteed to be the best algorithm possible out of all the algorithms there. If you try to look at a node and you try to say that, let me prune that, let an algorithm prune that, not discover that, it will be possible that the optimal route went through that and pruning that was really a bad choice. So, the A-star algorithm is called as the best algorithm possible, and remember, this is for a given heuristic function. You can still make it better by supplying a better heuristic function. And it's called as optimally efficient rather than optimal or the least computation time, because how can I assume that heuristic function calculation itself takes in a smallest amount of time which is possible. Now the other property about the A-star algorithm is BFS goes depth by depth, depth 0, depth 1, depth 2, depth 3, depth 4, depth 5. That's why it's optimal. Uniform cost search goes in cost contours. First all nodes with a cost of 0, then all nodes with a cost of epsilon, then all nodes with a cost of 2 epsilon, and so on. As you go along, the nodes increase their F value. A-star algorithm goes in increasing cost contours of the F value. So what did I do? I first processed all nodes with a F value of less than equal to 11, then all nodes with a F value less than equal to 12, then all nodes with a F value less than equal to 12, then all nodes with a F value of less than equal to 13, then all nodes with a F value of less than equal to 15. So it makes contours of F values. As I go along, I increase my F values. That is the actual way to prove that the algorithm is optimal. Proof, of course, I don't give it formally in this classes, but now you should be able to think, where is admissibility coming in making it optimal? So as you go towards the goal, the G value will only increase in the path, but the H value, what does it say? Will it reduce enough so as not to make this trend lose out? And then again, how can I be sure? Again, it's a food for thought to you, that how am I guaranteed, because of that triangle law of inequality, that I can never come up with a path with a cost which is better? So it happens because of the triangle law of inequality. The moment you took another route to come to a path, it will turn out to be bigger because of this triangle inequality in the H values. So that's how the optimality is actually decided for the A-star algorithm. Give it a food for thought for yourself, but the rationality is that these values will keep on increasing from the smallest at the source to the largest at the goal. That's what happens with every algorithm. That's why all these algorithms are optimal, except for the depth first search, of course.